when we talk about a function, we have an x-axis and a y-axis, and we usually write an equation, let's say, as y is equal to 4x plus 5. That's something like a simple line, something like this. But it doesn't have to be a line. It could be a quadratic. It could be any kind of function. But we're saying that x is the independent variable, y is the dependent variable, and these variables can represent different things. For example, I don't know, I guess we can talk about the distance to stop, or stopping distance to stop, or like I said, stopping distance, versus my speed. So if I'm driving a car, the faster I go, the faster my speed, the longer it'll take me to actually come to a complete stop. But sometimes I may want to talk about it from the other perspective. I may want to talk about it from, calculating the distance that it took me to stop, and then figuring out, well, what was my speed? So kind of when I'm recreating an accident scene, I would actually want to talk about it in terms of x being isolated, and it is the y that is in fact minus 5, or whatever the case is. The y is what is calculated. So I kind of want to look at it from a different perspective, where I want to flip the x and the y. And that's what the inverse function allows us to do. It allows us to switch around the x and the y and write things in terms of the new y, the inverse. So that's really why we're here. Okay, so essentially there's a few steps in figuring out the inverse, and these are the steps that have been outlined in class. And I know that I've taken time to explain some of these problems, but I'm just going to pick number 10 and just show you how I would do number 10 here. So number 10 really says that f of x is equal to x minus 9 all over 4. And the way we find an inverse is that first things first, we replace f of x with y, because that's really what f of x is. And then second step is to switch around the x and the y. So always the second step, and here I'm just going to take a nice little shortcut and erase stuff. And then almost the last step is to isolate this new y. So this y, how do we isolate it? So here I got to get rid of division by 4. And I'm going to do that by multiplying both sides by 4. That'll cancel it out. So now I'll have 4x is equal to y minus 9. And then I'm just going to bring the 9 over, and I'll end up with 4x plus 9 is equal to y. And that would be my inverse, but now, I mean, you can tell that, this y here looks no different than the original y. So I'm going to replace this y now with a notation that reminds me that this is my inverse, and that notation is f, and then this -1 is not an exponent, it's just a notation, f inverse x. And that is my final answer. So that's really what you're supposed to do. And yeah, look, we get the exact same answer that they've gotten. So we got it. We're here. We're on the right track. Now, one important property of inverse functions is if I put the inverse function inside of the original. And what does that really mean? Okay, so let's take a couple of these functions. So let's take number 10. We've got these two functions. So we have f of x is equal to x minus 9 over 4. So I could, in fact, try and find f of, let's say, 3. And what does that tell me? What am I supposed to do when I ask you to find f of 3? Well, I'm really asking you to replace every single x, and in this case I only have one x, every single x with 3. That's it. And then go ahead and solve. So over here, that f of 3 would really be equal to 3 minus 9 is, I guess, -6 over 4. And that's really -3 over 2. That's how I solve it. So the method is always the same. When you're given a value to find, you replace x with that value. Now, that doesn't have to be just a number, how I have here f of 3. I could, in fact, put anything I want inside of that bracket, right? So my question to you becomes, well, what if I throw in the inverse, right, which is 4x plus 9? So what if I put in the inverse inside of my original function? So that would be denoted as this, f of f inverse x. So what happens? Well, let's see. So instead of now, again, the inverse really is 4x plus 9. So that's really what I'm asking you to find. I'm saying find the original function if you plug in 4x plus 9 in it. So instead of writing x, I'm going to plug in 4x plus 9. And I hope you see that. If you don't, please continue to try these problems or watch my video again and ask me in class, because this is something that you definitely have to understand. So what happens when I do that? So my f of 4x plus 9, what will it become? And again, it's really f of the inverse. So I've put in the inverse instead of the original. What do I get? Well, in the numerator, I have 4x plus 9 minus 9. Well, plus 9 minus 9 cancels out. So I really just have 4x over 4. I cancel the 4's and I'm just left with x. And then you might say, oh, wow, well, that's really convenient. That's awesome. It happened in this case. But what if I told you that that's always the case? And you will get a question like that on the quiz. I will give you the original. I will give you the inverse. And I will ask you, well, what's this? What happens if you throw in the inverse inside of the original? And cool thing is, if you do it the other way around, if you throw in the original inside of the inverse, so if you find f inverse of f of x, you're also going to get x. So it's like awesome little shortcuts that you can figure out. Anyway, let's move on to the next set of problems. So a lot of these problems are asking, is this a function? Is this the inverse? So I'm not going to bother with that. 29 to 34 asks you if it's a one-to-one function. Again, go look through my class notes about one-to-one function. But really, a one-to-one means that a particular y-coordinate, let's say this y-coordinate here, I have two x's for the same y-coordinate. That makes it a many-to-one, because I have many x's to one y. All right? This function here is one-to-one. For any particular y, I only have one x. This one is also one-to-one. For any particular y, I only have one x. This one is a one-to-one, one-to-one, and one-to-one. So the only one that's a many-to-one is this parabola here in question 30. And then it also says, well, determine if it's a function. And to figure out if something is a one-to-one, you can do a horizontal line test. So that's kind of like a shortcut. You see, if I do a horizontal line test and if I fail it, I am not one-to-one. So this one here failed it because it touched the function twice. So this is the key. If the original function is many-to-one, its inverse will not be a function, because once you inverse it, you'll fail the vertical line test. And that's really if you fail the horizontal line test of the original, you will end up failing the vertical line test of the inverse, because essentially when you inverse things, the x becomes y. So a horizontal line, which is y is equal to 4, when you inverse that, becomes a vertical line, x is equal to 4, and you will fail the vertical line test if you fail the horizontal line test of the original. So the vertical line test of the inverse will be equivalent to a horizontal line test of the original function. I hope that makes sense. Again, if not, talk to me. You've got to send me an email and ask me to talk to you about this. Now, this many-to-one function in question number 30, I could make it a one-to-one. I really could. How could I do it? Well, how would I cut it in half? So if I take the vertex and I just draw the right of the vertex, let's say this here is x is equal to 2. If I just restrict my domain and say, well, I'm just going to draw this from x is equal to 2 and onwards, so that just means that my x would be greater than or equal to 2. I'm now restricting my domain, and that means that the left side of the parabola is non-existent. And if that's the case, then I'm going to pass a horizontal line test, and I will become a one-to-one function, which means that when I inverse a one-to-one function, I will still stay a function when I'm inversed. So that's how we can come around that trick. I'm going to pass some of these other problems. 69 to 78 really just say, hey, look, graph it. Graph these functions here and do just what I told you. So if I graph this here, x minus 2 squared, I mean, from your knowledge about functions, x minus 2, the minus 2 is really a shift to the right 2 units. So I'm right here, and it's a parabola. It's the exponent 2. So the question is, how do you make this into a one-to-one function? And it's literally what I just said. Cut it so that only a half of it shows. So let's cut it here. And I can really just say, well, let's say x to be less than or equal to 2, meaning that I'm going to cut anything to the right of it. And there we go. We've done it. We can do the same thing with all the other functions. And the question here says, look, just graph these. Graph these functions using Desmos, see what they look like, and then tell me how to make them one-to-one. So if I look at number 70, I know that it's going to be something like this. It's going to look like a parabola, but kind of like chunkier, like this. Something like this. So how can we make this a one-to-one function? Again, same thing, cut it. So we're going to cut it, I don't know, like, so I guess right along the y-axis, that's going to be the cutoff point. And let's cut the left side. So if I cut the left side, that means that x is now greater than or equal to 0 only. That's really how you cut things in math. You restrict the domain. We could restrict the range, but not in this case. In this case, it's the domain that has to be restricted. And yeah, that's just it. You cut it. You cut it in half. And that cutting really means that you're restricting the domain the way I just showed you. Okay, let's go into other functions. And here it's asking, okay, so look at this. Here it gives you a graph of f of x. And the graph of f of x really just has a bunch of points. I'm just going to zoom in a little bit more. So a graph of f of x, so if I graph, or if I just sketch these coordinates for x, I got 3. And when x is 3, y is also 3. When x is this coordinate here, when x is 1, y is 2. So this is the original function. This coordinate here has -1, -2 for the original function. And this coordinate here has -2 and then 1, 2, 3, 4, -4, I think. Right? So these are the coordinates of the original. And now they really, look, they don't want the original here. They want the inverse now. So I just have to flip them around. So when x is -4 in the inverse, well, that's the original y. That's this guy right here, right? The original y. So what's the inverse y going to be? Well, it's -2. I'm just switching these around, right? -2 for x of the inverse. Well, that was the y in the original. So that's this guy right here. The x is -1. 2 for x, but that's in the inverse. Again, it's the inverse. So that means the original, it was y. Now it's x, but it was y. So that means the x was 1. Now it's y. And then for x is equal to 3, the y is 3. That's this coordinate right there. I hope you get that. Try and do question number 80. And if you have issues with it, let me know. And then it says sketch the graph of the inverse. I'm going to let you do that. You can literally just sketch these coordinates. And you've got some x's and y's. And you're going to connect the dots when you're done. That's it. So now the next one, 81 to 88, I love this question. Let's see. So they're giving you y is equal to f of x and y is equal to g of x. And again, they're giving you a bunch of numbers, all right? Or a bunch of coordinates here. And as they're giving you the coordinates, they're saying, oh, guess what? Now you're going to have to figure out what this is and so on. So, I mean, they're asking you, the question number 81 is saying find the find the y value of the inverse when x is 0. Well, that really means, okay, so find the coordinate that has 0 in the original function would be y. I hope you get that. The original function would have 0 as the y because in the inverse, 0 is really the x, right? Because this is the inverse and that's the x. The 0 here is the x. I'm going to erase it because I've noticed that I'm getting maybe a bit too messy. But this here, this is your x, right? And the f minus 1 means that it's the inverse. So that means that it used to be y, right? In the original function, it was a y, and now it became an x. So they're asking for the coordinate. So let's go ahead and see. So in the original function, I had 0, 2, I guess, right? 0, 2, that's the coordinate. This was my x, and this was my y. I also, in the original function, had another coordinate, and let's say this is 0.5, 0. That's the coordinate. I'm thinking it's like 0.5, could be 1, but whatever. That was my x, was 0.5, and my y was 0. Now they're saying, well, if they're saying the inverse when x is 0, well, that used to be a y. So which one of these points do you think I'm looking at? This first one, 0, 2, or the second one, 0.5, 0? I hope you say the second one, because in the original function, whatever is the y used to be the x, right? Or will become the x, sorry. Whatever in the original was a y will become x in the inverse. So f negative 1 or f inverse at 0 is really equal to 0.5. I'm going to zoom out a wee bit. I hope you understand that. Okay, I'm going to erase this. I will not ask you the other questions, and just because I'm mindful of the time, I'm not going to do 83, 85, or 87. I would ask you to try and do 82, but I will ask you to look at this question, either 103 or 104. So first of all, 103 says is f1 to 1. Okay, so what does 1 to 1 mean? Well, I have an x and a y, and nothing repeats, right? Remember, a 1 to 1 means for every x, there's a single y. For a single y, there's only a single x. And here, that's true. So yeah, it is 1 to 1. For one y, there's only one x. That's the explanation. Nothing repeats. Find f of 11. So find the y value when x is 11. So, well, what's that? Well, that's 45, right? When x is 11, y is 45. Find f inverse of 43. So that means find the inverse when x is 43. Well, the inverse when x is 43 really means in the original, because that's the graph that I have, the y was 43 and x was something else. So now they're asking me to find, now they're making 43x and they're looking for the y, which again in the original was just flipped around, right? So the x was 43, and what was the y then? Well, y must have been 10. I won't ask you D or E, f of f inverse 41, but if I, let me just quickly kind of do it. So they're saying whenever you have these things that are in one thing inside of another, you're going to, I mean, you could use a shortcut that we talked about before, but we're first going to look at, and this x here is 41. So we're going to look at f inverse of 41. So what does that mean? The x here is 41, right? That's your x. That's of the inverse. So that means that it used to be y in the original. So let me find 41 on the y. So f inverse of 41 is really 8, right? So that's equal to 8. So this whole thing I can make equal to 8. And then they're asking me to find f of 8. Well, if I go look at f of 8, so they're asking me to find y now when x is 8, right? Because this is here, this is x. Well, that's really just 41. So the question is really just, or the answer is really just 41. And that kind of gets us back to the original shortcut that we talked about. We said f of inverse x is always equal to x. So you're always kind of going back in circles. You're going from x to y back to x. I'm going to ask you to do the last one on your own. F inverse of f of 13. Hopefully you recognize that that's just 13.